Okay, the third and final iteration. This is going to be about putting some of the pieces together and using tidyR with dplyr, using them together. For the sake of teaching and understanding, trying to convey some of these concepts, it's good to use small data sets and use kind of simplified code. But it's also a lot more helpful to give you some real world examples, okay? And so this is my attempt to try to do that, just to get you guys thinking a little bit, okay? So I'm going to use some real data with a project that we were just working on. I've got a graduate student working on this right now. And so we're generically looking, there's a lot of these natural gas pipelines getting installed in Ohio. And we are trying to evaluate, get a sense of what the impact that they have, the impact of installation, these pipeline installations, longer term impacts have on soil properties and then crop yield. So a lot of them are going through farmers' fields. There's a large amount of disturbance to install these subsurface pipelines. They dig these big ditches. They have huge equipment that goes back and forth. Trying to see that they go through and remediate these sites, but we're trying to evaluate if these pipeline impacts these pipeline installations have lasting impact. Okay, so let me introduce you to the data first, and I'm going to read this in, and I'm just going to show this to you right here, okay, as I walk you through some of the data. So there are the first three variables are ID variables, and this is kind of the reshape nomenclature of what an identifying variable is. And these are related to experimental design. So there's site ID, and there's 4 sites, A through D. There's treatment, which there's actually 2 treatments. There's ROW, which is the right-of-way. This is the area over the pipeline itself. So what was the pipeline was installed. And then adjacent. And so this is a non-impacted adjacent area. So our experimental design, and then there's replication. So there's 3 replications, 1 through 3, and it's along the pipeline transect. So we can imagine an experimental design where a pipeline was installed through a field. We went over that pipeline and picked 3 points along that pipeline transect. Then we moved out several hundred feet and selected additional points in a non-impacted adjacent area. So for every site, we essentially have 3 right-of-ways and 3 adjacents. Okay, that's our design. All right. So I've read this data set is on Carmen. If you want to download and follow along. I've read in the data here, the structure of the data. There's 24 observations and 22 variables. Okay. First thing I'm going to do, we'll see that some of the site ID was read in as character for the site ID and rep, and then, the first 2 variables are read in as characters, and the last one, the third one, is an integer. They're really all factors. We have 4 sites, 2 treatments, and 3 reps. So I'm going to use this new function, which we talked about mutate earlier, but this is mutate at, and this is just a kind of a fancy way to write over data. So we're going to mutate at df, and we're going to apply that to the 1 through 3 variables, the first 3 variables, and we're going to apply this function as factor. Again, we could pipe this, right? But there's df, and now if we look at the structure of the data, instead of characters and integers, they're all factors. And we can see there's factors with 4 levels, treatment factor with 2 levels, adjacent right of way, and then rep factor with 3 levels. Okay. All right. So now imagine we want to explore data and determine how pipeline installation impacted soils. Since there are many response variables with different units, for a first pass, it might be easier for us to standardize all variables just by taking a percent difference basis and examining. So just explain that our experimental design contains 3 paired sampling areas. There's a site ID, and then nested within each one of these site IDs, there is 3 right-of-ways and 3 adjacent, and those correspond to rep 1, 2, and 3. Okay. We're going to take a percent difference calculation, which is this right here. It's right-of-way, so that's the impacted area, minus our adjacent, which is our serving as our control, and then we divide by our control. So this is what would be considered a, just a kind of a classic percent difference calc. So it's new value minus old value, and then that difference divided by the old value or the control, and we multiply this by 100 to turn it into a percent. All right. We want to do that with all variables, okay? But here are the structure of the data, right? We've got different sites, treatments, and reps. So how do we want to do this? Now, the site is kind of quasi-replicated. There's 3 observations for site, 3 observations for the right-of-way, and 3 corresponding observations for the adjacent. So we actually want to take and calculate a percent difference really on a per rep basis, because we know that there's a lot of spatial variability, and we have replicated it intentionally to try to account for that and then give us confidence in what we find. Okay, so one option would be just to average the right-of-way, average the adjacent values, and then take the percent difference. But it's probably a little bit more robust because of the spatial variability that we encounter, that we do this on a per rep basis. So in other words, I want to take the soil moisture at site ID A, treatment right-of-way at rep 1, and then calculate that as a percent difference from this control of A adjacent rep 1 here, okay? So how do we do this? It's complicated, right? Like this is, if this is in Excel, we could, and we've got 22 variables. Here's only the first, say, handful. Imagine, actually, I've shrunk this data set down. We have 24 sites, and we've got, I don't know, probably about 65 variables that we've measured. So there's just a lot here. And imagine doing this in Excel would be challenging to do, right? You'd have to sort and do things, and and then recompiling that together. Good news is that R is here, and there's lots of efficient ways that we can do this. Okay, this is one way. So we can create a for loop with conditionals in R to match each site rep variable combination, but this is complicated. It takes time to set up. I'm not very good at it at all, to be perfectly honest. And maybe well, anyways, it's just something that I'm not terribly great at, and often get, error messages that I don't really understand. So another approach could be to restructure the data and then perform calculations across the data. So this is what we have opted to do. Okay. So again, going back to last week, we're going to use tidyR to do this, okay? So the first thing we want to do, again, here's the nature of the data. We want to stack all variables. That's all we're going to do. We've got variable moisture, variable, and these data are tidy, but they're not in a form or a structure that, even though they're tidy, hooray for being tidy. And well, I won't go back and bore you with what we define as tidy, but they're tidy and they're ready to go, but they're not in a way that we can do these kind of manipulations that we want to do in terms of taking kind of an integrative percent difference calculation. Okay, so all that being said, let's go back, and we'll have to think back to last week and think about pivot longer. So we're creating an R object called df long. So we're going to take our data frame and put it into this long format. We're going to apply the function pivot longer, we're going to apply it to our data frame df, okay? And then we are going to omit the first 3 rows because these are essentially ID rows, right? And we're going to say names to variable. So we're going to, what does this mean here exactly? Can you remember? We can call this anything we want. I'm calling it variable and value just because that's what reshape uses, and actually reshape uses lowercase v's for variable and value, but this might help. But we can call it, honestly, anything we want. So we're saying the names of these variables here are going to get stored in a new column called variable, and the corresponding values, all this, the good stuff, the measured response variables, are going to get stored into another column called value. Okay, so we run this code, and what's happened? Well, since we've told it that the first 1 through 3 variables are ID variables, it's retained those. But again, our variable, which contains the variable then, and then here's the value. All right, so if we go up, and let me just do this real quick. Moisture 21.3, 21.3. Clay 15.4, 15.4. Sand 13.3, 13.3, so on and on. So it's taken this first row of observations and it's basically transposed it, okay? If you want to think of it that way, it's transposed it down from a row of observations to a column of observations. And then it's taken and it's done this for every single one. So we, again, haven't, this appends it at 10 observations. It only prints out 10, but there's 446 more rows here. So if we go back to, just to be sure we know what's going on, we can say structure of df. There's 22 total variables here, 22 variables. There's actually 19 that are response variables. Okay, so these 19, 22 minus 3 is 19. And there's 24 observations. So if we say 19 times 24, we get 456. So, but what if we do the dimensions of df and the dimensions of df long? So the dimensions of df long are, there's now 456 observations, which just so happens to be the number of response variables times the number of observations, right? So it's just put those in a single long string of values that we happen to call that variable value right here. And then these are the corresponding things. So we'll hit 24 rows. At 24 rows, moisture, clay, sand, silt will start over, but presumably this will stay the treatment, and site ID will stay the same, and rep will change to 2 because that's the order that it appears in the original data frame. All right. Hopefully you're on board here with all that babbling. Okay. Now this should look familiar. It should, because we talked about it last week with reshape. And here we have melt. Okay, so it's very similar to what melting is. Now I'm just doing this. We've got reshape loaded just for the sake of kind of putting these pieces together and showing you some of the similarities. Melt .df. We're going to melt the data frame, and IDs are 1 through 3, right? So here it is. And if we look at the first 10 observations in melt, it's doing the same thing, although it's sorting it a little bit differently. So pivot longer and melt vary just a tad bit in the sort, but they can produce identical output. In this case, they have, right? And so just to give you, to show that, to demonstrate that to you, you can see that the dimensions are identical for df long and df melt. They're both 456 observations by 5 variables. And then if we do just a little bit of sorting with this arrange, we can see that head df long and head df melt are really identical observations in terms of what they've done. So here, let's see, the melt has rounded things up because it's actually done, well, no, not because it, I don't know why, but it just has placed additional decimal places on there, whereas the pivot longer has not. Okay, but these are the same values, right? Moisture, clay, you can take a look at that. All right, so we've made it longer. We've made it into one common string. Now we want to restructure. Okay. So then here's the rub. This is the tricky part to try to figure out what we're doing. We want to split by treatment because we want to take, again, what we're doing is we're going to calculate a percent difference. And we want to take the corresponding site ID and rep, and then take the row, the right of way versus the adjacent, and do this percent difference calculation. Okay. So we now will employ pivot wider. So we did pivot longer, and we're going to do pivot wider to basically split these columns up by treatment. Now, again, if we look at, DF long, we've got adjacent, and then it, shifts to right of way or shifts to ref 2. And there's all these observations that are essentially stacked on each other. Now we're essentially trying to restructure the data. And this is really the value of tidyR and just kind of reshaping data in ways. So let's follow the code. We're creating an R object called df data frame wide. We're going to apply the function pivot wider to our elongated data frame, right? So we're now putting it here. And let's just pull up this right here, df long, just so we can see. So this is our df long. Our names are coming from treatment. Okay, again, the names from, that means essentially we're going to create, we're making it wider. So we're going to create a wide data frame, and we're going to use the variable names. The variable names are going to come from this column called treatment, TRT. Just so happens in this scenario that we only have, we only have 2 treatment levels, right of way and adjacent. And then the values are coming from our value here, okay? If we wanted to put it back in the exact same order we found it, well, maybe oh gosh, we could, always turn this into variable, right? And this would give us the exact same data frame we started with. 24 observations and 22 variables. But that's not what we want. We just melted this stupid thing, or we made it longer to try to reformat it. So we don't actually want that. We don't want it to be the original way. We want it to be different. And so here we're using TRT. And again, this TRT or treatment only has 2. So we're splitting it up into 2 separate columns based on the treatment, right? So then if we do that, now look what's happened. Now we've got the same 3 ID variables, site ID, rep, and variable, but now our columns are right of way and adjacent, okay? And so this is beautiful because it's taken your 456, our dimensions, which was 456 up here, divided by 2, and it's now 228, which is exactly how long this table is. So it's 228. So there's 228 observations that are designated as right of way and 228 as adjacent. And awesomely, site ID and rep all match up, okay? So again, I say note the dimensions, 456 for your long and 228 for your wide. We can check we can pull up this view.df and check that our this df wide is actually structured in a way like, I always recommend that people do this to make sure that what you think R is doing, all these automated fancy steps, that's actually doing what you think you're doing, right? So here we've got moisture at 21.3. Here it is, our first observation, 21.3. The adjacent, 22.6. Site A adjacent, rep 1, 22.6. So that looks good. Clay, 15.4, 13.6 down here, okay? So on and on it goes. It basically is comparing these two treatments together. All right, okay, so that's helpful. That's what we want. So why do we want that? Well, before I get there, let's talk about, we can also do the same thing by casting, right? We talked about this last week. Just look at this piece here. We're going to cast our df melted function. And we're going to say, a lot of our calls last week would say something like site ID plus rep plus treatment, and then this tilde variable. But what happens if we put the treatment on this side and the variable on that side, okay? And then we can take the mean or the sum. It doesn't really matter in this case. But if we did this, it would restructure the data in the same way that we've done with pivot wider. When we've got site IDs and reps and variables, and then our adjacent or right away. Interestingly, cast puts adjacent first and then row, the right of way, and then pivot wider does not sort first. So it's right away first, because that's the first thing it encountered in the data frame was this right of way and adjacent. So there's just some subtle differences between pivot longer and reshape and pivot wider and cast. But like we already talked about, same, okay? I could run the same thing here and call it sum. Since it's not actually doing any aggregation, this cast function, recall that cast is typically used for aggregating data, whereas pivot wider and pivot longer is just restructuring the data. So here we're basically kind of tricking R to sum it or to take the mean. There's only one observation, so that's your value, right? But these calls are identical, except one says mean and one says sum, and it produces identical output with cast. All right. So let's go back to our df wide. Okay, so df.y, this is what we want. Now, what we're going to do is we're going to do our calculation, because everything's lined up and it's a lot easier to do a kind of an integrative calculation when it's like this. Okay, so this is something, what we're going to do is we're going to create a new variable called PD for percent difference. So we're going to append that variable as another column or another variable on this df data frame or tibble. We're going to do that calculation we talked about, right of way minus adjacent divided by adjacent times 100. Okay, so we do this, and now here's our percent difference. Bada boom, bada bing. So now we have for every replicate, and for every site rep variable combination, we've got a percent difference that basically integrates the value of the right of way and the value of the adjacent, and helps kind of normalize or standardize that into a percent difference. Okay. Again, just just for the sake, try to imagine doing that in Excel. Now I've talked a lot here, but if we think about what we actually did to get there, I'm kind of complicating the story a teeny bit with the melt and cast analogy, but all we really did, we read the data in. Okay, let's go back to it. We read the data in, we mutated it to convert the first three to factors. We did one pivot longer step, and then we did one pivot wider step. And that's it. And then we did our percent difference calculation. So those were the steps that we did. It's really just a handful of steps here, okay? And it's all right here and it's all aggregated. Imagine if we were trying to do this in Excel, and then, we can, of course, we can do calculations, this equals this and drag, fill down, and then, but you've got to bring all that together. It's just, it's a lot more complicated, a lot more time intensive. And more importantly than both of those things, a lot more error prone. When you're copying and pasting and doing formulas in Excel, there's a lot of challenges with that. So, okay. Now we've got, for every replication, we've got a percent difference. But imagine we want to take the average for every site. So we've got for site A, I've got a percent difference for moisture, soil moisture, rep 1, 2, and 3. And maybe I actually want to take the average of those things, okay? Or same, same with any of these variables. Say there's total carbon, and maybe we actually just want to take an average so we can see what's going on with that site, okay? So here's something I do quite commonly, which is I basically create two functions for dealing with missing data. So this is really just, it's average, it's a mean. I'm just taking the mean or the average. So I'm saying creating a function x, mean of x, and NA remove equals true. So we're explicitly saying remove the missing values. And the same thing, this is a standard error function. You can look at some of this. I'm not going to spend time on this right now, but basically just two functions for average and standard error. You can see that they're stored as functions down here now. And it just helps a little bit when you're kind of running with data and have, sometimes you encounter missing variables, and it tells R more explicitly how to deal with NA removes, NA values, we're going to remove them true. And then the standard error, if there is a missing value, it won't just blow the standard error up. It will tell it to divide it by not the total number of observations, the total number of observations that are not NA values. Okay, so anyways, moving on from that, you'll just have to, you're welcome to use these. You just have to take my word that this is basically just taking the average and the standard error. Okay, so now, again, we've got for each, and this pivot wider, or df.wide, we've got 3 reps for moisture for any given site, 3 reps for clay for any given site. In other words, any given variable, any given site, there are 3 replicates, and we want to take, say, the average and the standard error of those. Okay, so let's pull some of this together. All right, and I'm creating this obnoxiously long R object called average by site dot variable. Okay, and we're going to take the dfy, that's what we're looking at right here, our dfy with our percent difference calculation. We're going to group by site ID and variable. In other words, for every site and variable combination, we want this calculation to be done. We're going to summarize it. We're going to say, we're going to create our variable called average PD, average underscore PD. It could be average dot, it could be average dash, whatever we wanted to do. And then we're going to take AVG, which is our mean value, right? This is this average function. And we're going to apply that to our percent difference. Likewise, we're going to take standard error and apply that function to our percent difference. And for every site variable combination, we're going to call this SE underscore PD, standard error of the percent difference, average of the percent difference. And then we're going to do it all with piping. Hooray for piping. So df wide, group by, summarize. That's the steps, right? We get this message here. I don't entirely understand it, to be perfectly honest, but it's not an error, it's just a message. And then if we ask to return, Now we've got a tibble with not, again, our dimensions of df wide were 228. And now our tibble for our average by site is 76, okay? So 228 divided by 76 is 3 replications, right? All right, so now we've got, again, the rep is gone. The rep variable is gone because it wasn't explicitly called, right? And we've averaged over those 3 reps, and we've reduced the structure of the data frame from 228 observations by 6 variables to now it's 76 by 4, okay? So these are averaged for every given variable site combination. And you'll also see with that group by function, it's now sorted variables. So now it's not moisture, clay, sand. It's actually sorted in alphabetical order. Okay. So for better or for worse, you might not want that. You can turn those functions off, the sorting, or do some remerging with an original vector. There's lots of ways to handle that. Okay. So what next? Now that we've got kind of what we wanted an average % difference in standard error based on every site variable combination. Well, what next? Well, it depends what we want to do. Of course, we can export it, right? We can export it as a .csv file. That's what this line of code does. We can graph it. So we'll get into graphing next week. But here's, and I'm not going to spend time explaining this code here, but we could, of course, send this to ggplot and graph all the averages. This is asking for Y is our average PD and X is our site ID. So our sites, A, B, C, D, and then this is the % difference. So we can quickly just kind of look at our variables and see, which ones, these are all scaled the same from 100 to minus 100. We can see which ones had a greater effect and if that was a consistent effect across sites, et cetera, et cetera. So this helps with data exploration, just some outlier detection, et cetera, et cetera. And then finally, we could think about restructuring our data into a wide format for a table so that each site is a separate row. This might be something more applicable to a manuscript. Okay, so let's look at this. And part of the kind of the iterative nature of this is just showing you that there's a lot of things that you can do here. So we've aggregated the data. This is aggregated data, averaged by site dot variable. Okay, so here we're gonna create basically a new R object that's just 2, generically averaged by site variable 2. We're gonna pivot wider. We're gonna apply that to average dot site dot variable. We're gonna say take our names from variable, this column called variable, okay? So in other words, we're trying to get all the variables as unique columns in this data frame. And we're going to take our values from not just your average, not just the third variable, but we want to retain that standard error to both the average and standard error, okay? So if we run that, and see what that output looks like. So here it is. It's not that pretty, but we've got our 4 sites as rows, A, B, C, D, and then we've got our average % difference for buffer pH, or average % difference for carbon, or average % difference for calcium, for clay, potassium, on and on. And you can see there's 30 more variables here that then were printed. And then after we get through all the averages, the standard errors come in. And so then we can export this table again using, this is using pivot wider just to kind of restructure some of that output, if that's helpful, right? Maybe it's not. We could say, in the same vein, let's just show this real quick again. We could say take the names from site ID and the values from 3 and 4. And let's see what that looks like. Well, now we've got our average percent difference for A, for B, C, and D, and then our standard error for A, B, C, and D. And then our variables are now our rows, okay? So depending on how you wanted to structure this, there's a lot of different options. Okay, so, and, I make the point here, and with piping, you could do all of these steps in a single call, one call, and it could do, it would do all this where you import data. The steps would be, again, you import data, you convert things to factors, then you stack it, then you restructure it with this pivot wider, you stack it with pivot longer, restructure it with pivot wider, calculate your percent difference. You can go overboard, and sorry, I'm just keep scrolling here. Go overboard and really pipe everything, not everything per se, but a lot of things can be piped, and that's can be very helpful, but it's often a lot easier, especially when you're getting started, to break your code up into more digestible nuggets. And it's no problem, if you've got these A, B's, and C's stored here, unless you've got huge data sets that are taking up lots of memory, it's usually not a major issue. Okay, I'm going to stop there. We've got homework that I'll post, and it's going to be using weather data and just give you some experience with a different type of data. So again, the whole point, hopefully at this point, you might be a teeny bit confused, but feel free to go over the code, slow down a little bit, and just see how, and just envision, if you will, how tidyR and dplyr can work together, where you can restructure data, you can aggregate things, you can take, averages or percent differences, like whatever there's a lot of different things that you can do with this. It's just a really nice, powerful suite of tools to help you basically restructure and manipulate data.